are compulsory. Okay, so in the previous lecture, basically we discussed some results regarding the subspace when subspace is closed or complete. So whenever we have a non-linear space and whenever we consider its finite dimensional subspace, then that is always complete. And moreover, we have the result regarding the convergence of a sequence. So every sequence will decompose. We can write as a linear combination of the basis element, and that gives us corresponding m sequences. So xn converges if and only if this m sequences converges, and similarly for boundedness. So we discuss one part, other part I have given as an exercise, and then we discuss one important example, that is the L infinity as a subspace which is not complete. That is basically the infinite dimensional subspace, and that is the subspace of all sequences which has only finitely many non-zero terms. So we have discussed that is a that in which in C00 we have a sequence which is Cauchy but it is not convergent. So therefore C00 is not complete. And then we revise one result of matrix spaces. So in matrix spaces, compactness is characterized by sequential compactness, right? And the Hannah-Borel property, that is a subset of matrix space is compact if and only if it is closed and bounded. So we are going to use these results in study of the compact of the unit sphere in the nonlinear space. So for that we need a very important result that is known as Riesz lemma. So that is what we are going to discuss today. So this result is known as Riesz lemma. So Riesz lemma is regarding basically the quotient norm. So let us start with the we know that whenever we are discussing the quotient norm, we are taking Y as a closed subspace of a non-linear space. So let X be a non-linear space and we have a closed subspace of X. So in this case, so this result is regarding the number R between 0 and 1. So let us fix that number. So whenever we have a number between 0 and 1, R is the number between 0 and 1, right? Like a geometric series. So whenever we have a number between 0 and 1, you can find a vector xr in X such that xr is on the unit sphere. So unit sphere means its norm is 1, right? So in non-linear space, whenever an element has norm 1, we will say that it is on the unit sphere, right? So in R2 we know that whenever norm is 1, that is on the unit circle, but in R3 whenever the set of all vectors of norm 1, that lies on the sphere because it is a 3-dimension, right? So therefore the vector which has norm 1 we say all those vectors are basically on the unit sphere. So unit sphere means basically the set of all x such that norm x is 1. Right. So like unit pole, we can define unit sphere. So what this result says that whenever we have a closed subset y of x and the number 0, number r between 0 and 1, there exists xr on the unit sphere such that r is less than or equals to distance of xr with y less than or equals to 1. So what this result says? This result says that we are given y which is a closed subspace of a nonlinear space x, and we have a number r between 0 and 1, then we can find a vector of norm 1 in x such that the distance of xr with each element of y is bigger than equals to r, right? R is this number. So basically we are finding a vector xr which is r distance away from y, from each element y, each element in y. So this is the statement of Riesz lemma. We want to prove this result. So to prove this result, first thing is clear that whenever we can find such a vector, we will always get this part. So that is always true. So note that whenever such vector xr exists in x, so such vectors means that means its norm is 1. So whenever we have a vector in x whose norm is 1, its distance with y, so distance of xr with y, so what is the definition? By definition it is infimum, right? So that is infimum of norm of xr minus y, y belongs to capital Y. And then we know that every subspace contains a zero vector. So that means when we substitute this 0, this is the infimum, so it is less than or equals to all elements of this set. In particular, when we substitute y equals to 0, the corresponding element is xr minus 0, that is norm of xr. Right, so this distance is always less than equals to xr because every subspace y contains 0 element, and then norm of xr is 1. Right, we have a vector whose norm is 1. So that means distance is always less than or equals to 1. So we have not proved that xr exists, but what we are saying is whenever xr exists, whose norm is 1, we'll always get this part. So only thing we need to prove is we need to prove that r is less than or equals to distance of xr with y. Right. So only thing we need to prove here is for 0 less than r less than 1, there exists xr such that its norm is 1 and r less than or equals to distance of xr with y. Okay, so let us try to prove that part. So to prove that part, we need to assume that, yeah, so here what is y? Y is a not only a closed subspace, but it is a proper closed subspace. That is important here. So we cannot take y is equals to x, right? Y is a proper subspace of x. We are going to use that. in the proof. So since y is proper subspace, y is not equals to x, and that means there exists at least one vector which is, because y is a subspace, so y is a subset of x, but y is not equals to x. That means x has some vector which is not in y. So there exists x in x such that x is not in y. Right. So basically, x is the element of y complement, x minus y. So since x belongs to y complement and y is close, so what can we say about distance of x with y? Y is a closed subset, and x is not belongs to y. So distance of x with y is, can it be 0? We studied some properties of distance in terms of y is closed.
Sir, distance of x from y is equal to the infimum of distance of the point x from every point of y. The infimum.
Mm-hmm. Yeah, so my question is that if x is y is closed, that is given, and we know that x is in y complement. So can this will be 0?
Since y is closed, then it will also contain its limit point. So no, sir, it can't be 0.
It can't be that, right? Because distance is 0. We mentioned one result that distance is 0 if and only if x belongs to y. So this is true whenever y is close. But now we know that x is not in y. That means distance cannot be 0. And we know that distance is always non-negative. So that means distance is strictly greater than 0. Okay. So this here we are using y is closed. Right? Y is a closed subspace. So that we are using. So now we have a distance of x with a closed set strictly greater than 0. So now we will use the definition of infimum, right? So since 0 less than r less than 1, distance of x with y and distance of x with y by r. So which one is bigger? 0 less than r less than 1. So whether distance of xy is bigger or distance of xy by r is bigger?
Second one.
Second one, right? So this is less than this, and then now we know that this is basically the infimum of norm of x minus y, y belongs to y. So whenever we take a number which is bigger than infimum, there is always exists some element so that the corresponding element norm of x minus that element is smaller than the bigger number. Right. So since this holds, this is less than this, and then using the definition of infimum, there exists an element. So now this element which exists y, that actually depends on r. So therefore we are denoting this element as, yeah, first of all we are denoting y naught, but later on we will say it depends on r. So there exists y naught in y such that norm of x minus y naught is less than distance of x with y by r. Right, so that here we are using the definition of infimum, and then what we can do, we actually want this inequality, r less than something, right? So let us take r on the left side. If we take r on the left side, we get r less than distance of x with y divided by x minus y naught. So here we are dividing by x minus y naught because y naught, yeah, why? Because x is not element of y, right? X is in the y complement. So that means x is not equals to y naught. So x is not equals to y naught, and since x is not equals to y naught, we get norm of x minus y naught non-zero. X is not y naught, that means x minus y naught is a non-zero vector, so its norm is also non-zero. So therefore we can divide by non-zero number. So now we got this thing, and then note that the distance of x with y is basically infimum of norm of x minus y, y belongs to y. So that means if you want to write this again, what we can do is we can write as x minus y naught plus y naught minus y. Just adding and subtracting y naught, and then we can rewrite this as norm of x minus y naught, and so this element does not depend on y, but this element depends on y. So instead of writing y naught minus y, we can write it as plus y dash, where y dash belongs to y. So again here we are using that y is a subspace. So y is a subspace means basically y naught plus y is y. Right. So this is a property of quotient space that we use here. So that is what we are using. So what is the last quantity? Last quantity is that infimum of this vector with y, and that is nothing but distance of x minus y naught with capital Y. So distance of x with y is x minus y naught with y. So let us substitute this here. So in this equation, if we replace that, then we get, therefore r less than distance of x with y divided by x minus y naught, that is same as distance of x minus y naught with y divided by x minus y naught. Now this is a scalar, this is a number, so we can take it inside the infimum. So that is 1 upon norm of x minus y naught infimum of x minus y naught plus y dash. So this number we can take inside infimum, so we get norm of x minus y naught divided by x minus y naught plus y dash, right? Any scalar we can, using positive scalar, we can take inside infimum. And then whatever element, this element we got, that element we will call XR because it has a norm 1, right? What we want an element whose norm is 1 and its distance from y is bigger than r. So that is what we want, and we got it. So this is basically infimum of norm of xr, sorry, yr. Yeah, so it is xr plus y dash. Y dash belongs to y. So what is this? This is distance of xr with capital Y, and that is bigger than r, right? So what is xr? Xr is, we are denoting the element x minus y naught divided by x minus y naught norm. So therefore norm of xr is norm of x minus y naught divided by x minus y naught. So this is a unit vector anyway. So we are done. Yeah, so let us revise this once again. So we are looking for a vector in x whose norm is 1 and its distance from y is bigger than r, right? So if we can find such a vector, then the second inequality follows, so that we already discussed. And in finding that number xr, what we have assumed is y is a proper subspace, so distance is positive. So whatever r we take between 0 and 1, so r can be half, r can be 1 by 3, whatever number. So in that case, distance of xy is less than distance of xy by r. So using infimum definition, there is always y naught exists such that norm of x minus y naught is less than distance of xy divided by r. And then we can divide by x minus cross multiplying kind of thing. So r we have taken on left side and norm element we have divided on the other side. And then we have used the property of the distance function. So distance of x with y is always distance of x minus y naught with y for every element y naught in capital Y. So that we are using, and then r is less than distance of xy divided by norm of x minus y naught. Yeah, so then norm we can take inside the infimum. So that is exactly the element xr. So now we have found the element whose norm is 1 and r is strictly less than this element, right? So in fact, in the statement we are saying it is less than or equals to, but we are actually proving it is strictly less than, r is less than. So this result is very important whenever we want to say that whenever we have a proper subspace and we want an element which is r distance away from the subspace, such a result will be useful. So as a first application of this result, we want to study the when the closed unit ball is compact. So if X is a nonlinear space, then the following statements are equivalent. So the first statement is that every closed and bounded subset is compact. So that is essentially the Hannah-Borel property, right? So every closed and bounded subset of X is compact. So X is the full space we are discussing, right? We are not discussing the any subset of X, any subspace of X. We are discussing X is a given nonlinear space. Any closed and bounded subset of X is compact. So when such a thing happens, it happens whenever the unit ball is compact. So the second condition is that the closeness was there in the first part also. The closed unit ball. So closed unit ball means the set of all elements X in X such that norm of X is less than or equals to 1. So this is compact. So we are calling it ball, but it depends on what is the space and what is the norm. So if we take X to be R2 and the use an Euclidean norm, then this set is not a ball geometrically. It is actually a interior of unit circle, right? So closed unit disk. Usually we call it closed unit disk. But in general, if we take arbitrary nonlinear space, then such a set we call closed unit ball, right? So that is a general terminology in nonlinear space, and so this is the second condition. Third condition is X is finite dimensional. So this is, in some sense, this result is a characterization of a nonlinear space when it is a finite dimensional. So we can use this result as if the nonlinear space is infinite dimensional, then closed unit ball is not compact. Okay, so the first part is very simple. One, we are going to show that these three statements are equivalent. So first, 1 implies 2 is trivial because closed unit ball is closed as well as bounded set, right? So the first part says that it is a compact. So first 1 implies 2 is trivial. Let us try to prove 2 implies 3. So in 2 implies 3, essentially we are going to use the Riesz lemma. So what we are going to prove, we want to prove the third condition, so that is X is finite dimensional. So we'll prove this by contradiction method. So for that we assume that suppose X is not finite dimensional, so that means X is a infinite dimensional. So suppose X is infinite dimensional. So since it is infinite dimensional, it it will have a infinite dimensional linearly independent set. Right? It may happen that we cannot find its basis, but we can always find an infinite linearly independent set because it is an infinite dimensional set. So then there exists an infinite set y1, y2, y3, so on, which is Li. Right. So for example, when we discuss the set of all polynomials, then we have discussed that it contains infinite. Yeah. Just a minute. I have a call from HOD. Okay, so sorry for that. So basically, yeah. So when we discuss the polynomials, set of all polynomials, we discuss that it has a infinite linearly independent set. Basically 1x, x square, and so on. So this set is linearly independent subset of the set of all polynomials. So infinite dimensional vector space always contains a set which is infinite and it contains the set of linearly independent elements. So now consider the sets. So now define let yn, capital Yn that we are defining is a span of the first n elements y1, y2, yn. Right. So in this infinite set, we are taking y1, y2, yn element only in the capital Yn set. So this Yn we are defining for all natural number. So now what does this implies? So clearly Yn is a proper subset of subspace of X. So span means linear span we are taking, right? So set of all linear combinations of y1, y2, yn. So capital Yn itself is a subspace of X, which is the infinite dimensional nonlinear space, and it is a proper because Yn is finite dimensional and X is infinite dimensional. So Yn is a proper subset of X. So now we can use Riesz lemma. Right. So what is Yn? Yn is basically increasing sequence of subspaces. Y1 is contained in Y2, contained in Y3, so on. Right. So therefore, for each natural number n, What is the Riesz lemma? Riesz lemma says that if you choose any number between 0 and 1, so let us take half, r is equals to half, then there is an element xr in x such that its norm is 1, right? Its norm is 1, and its distance from xr is greater than equals to r is half. That means it is greater than equals to half, right? So for each n belongs to n, yn is a proper subspace of yn plus 1, right? Therefore, by Riesz lemma, for r is equals to half, there exists xr belongs to the bigger space yn plus 1. So this xr we will call xn because it depends on n, right? For every n we are choosing one vector. So there exists one vector in yn plus 1 such that is on the unit sphere. So that means its norm is 1 and r is less than equals to distance of xr. So xr is xn with y. So what is y? Y is yn and r is half. Alright, so instead of comparing x and y, we are comparing yn and yn plus 1. So for example, y1 is a proper subspace of y2 because y2 is two-dimensional, y1 is one-dimensional, so it is proper. So there exists one vector here whose norm is 1 such that its distance from y1 is greater than equals to half. Similarly, for every n we can do this. Yeah, so in particular, so xn is in yn plus 1, so xn minus 1 belongs to yn. What we get is 1 by 2 is less than equals to norm of xn with xn minus 1. So this holds for all k 1, 2 up to n minus 1. Right. So for each n, if xn is less than equals to n, then this holds. Right. So that is in general. If we take any two different numbers, moreover, for two natural numbers such that m is not equals to n, we get norm of xn minus xm is greater than equals to half. Right, because if k is less than equals to n, this holds. If k is bigger than equals to n, also this holds by the same property. So just switching x, n and k, this holds. So why this is important? Because this says that if xn and xm are different, they are half away. Right, distance of xn and xm is at least half. So that means what? And each xn has norm 1. Right, each xn has norm 1. So we have an element on the unit sphere whose infinitely many elements whose distance from each other is at least half. So therefore xn cannot have a convergent subsequence. Right, because if xn has a convergent subsequence, then in that subsequence the elements will be as close as we like. But this equation says that the elements are at least half away, right? Half distance away. So it cannot have a convergent subsequence, and that says all these elements are in the closed unit disk. So in closed unit disk we have a sequence xn which does not have a convergent subsequence. That means closed unit disk is not compact. So this contradiction contradict the assumption of 2, right? We are proving 2 implies 3. So second condition is that closed unit ball is compact. But what we got is closed unit ball is not compact. Right. So this is a contradiction which arises from our assumption that X is infinite dimensional, right? So therefore X is not infinite dimensional, X is finite dimensional. So we proved 2 implies 3 by assuming the closed unit ball is compact. We proved X is finite dimensional. Now the last condition, that if X is finite dimensional, then every closed and bounded subset is compact. So that we want to prove, and there we will use the Bolzano-Weierstrass theorem. So let us just recall. So Bolzano Weierstrass theorem, so, or property that says that every bounded infinite sequence has a convergent subsequence. So that is a basically sequential compactness. So what is sequential compactness? Every bounded infinite sequence in K has a convergent subsequence. So this is a Bolzano-Weierstrass theorem on real or complex number. So that we are going to use here. So let us start by assuming that X is a finite dimensional. So let X be a finite dimensional non-linear space. So whenever we assume it is a finite dimensional, it has a basis elements. Right. So let y1, y2, ym be a basis of x. So now to prove that every, what we want to prove, we want to prove that every bounded set what is the first property? Every closed and bounded set is compact, right? So that is what we want to prove. So let us start with closed and bounded subset. Let E be a closed and bounded subset of X. So to prove it is compact, we will show that every sequence has a convergent subsequence. Right? Every sequence in E, so E is already bounded. So every sequence in E has a convergent subsequence. To prove E is compact, we show that given sequence xn in E has a convergent subsequence. Yeah. So xn is a sequence in E, but E is bounded. Right. So if E is bounded, xn itself is a bounded. Right. So let us start with the decomposition of xn. So we know that each xn we can write as linear combination of the basis element y1, y2, ym. So that is kn1 y1 plus kn2 y2 knm ym. Right. And then we know that every property of the sequence we can prove in terms of this m subsequences. Right. So xn is bounded if and only if each of this m sequence is bounded, and xn is convergent if and only if each of these is convergent. So note that xn belongs to E and E is bounded in X, right? So therefore xn is a bounded sequence in nonlinear space X, and since xn is bounded, therefore the corresponding sequence k and m is bounded in K for all m is equals to 1 to plus j. We need to take j. J is equals to 1 to m. Okay, so each of these sequence is bounded, and then we know that by the Bolzano-Weierstrass theorem, by passing from one sequence to another, one subsequence to another subsequence, we can find a common subsequence which converges for each j. Right. So if this converges to for each j coordinate, then we know that the corresponding subsequence in xn converges. Okay, so this last part, okay, so yeah, so last part is easy, but I've taken a bit speedy. So yeah, so you just go through it. If there is any doubt, we will discuss in the next lecture on Thursday.